Hi, I'm Michael Marthaler, the CEO of HQS. HQS is a company located in Karlsruhe, Germany, and I'm very happy to talk to you today about a very interesting topic, quantum technologies, or more precisely about quantum computing. And all this, of course, in a very important context, that is global warming. Let me start with some words about myself. I have worked in the field of quantum computing since 2005. First, I made my PhD in Karlsruhe at the Karlsruhe Institute of Technology. And then I worked at various institutions in Japan, at the University of Saarland, and again at the Karlsruhe Institute of Technology. And then in 2017, I felt that the quantum computing hardware had progressed to a point that it became very interesting and important to work on the question about actual applications for quantum computers. And, of course, at this point, there were already many ideas of what to do with quantum computers. People had started to work on quantum computers because there had been ideas of what to do with them. But as you can imagine, the kind of path from writing an academic paper about what you hypothetically could do with a quantum computer to actually making this work is a really long path. And therefore, in 2017, it seemed to me that this would be something very interesting to do. And to pursue this goal, I founded HQS together with 3 of my former students. And at HQS, we make software to accelerate material and device development through microscopic simulation. And this topic is directly and strongly related to quantum computing, since we need to solve the laws of quantum mechanics if we want to understand microscopic phenomena. And quantum computers are pretty good if you want to solve the laws of quantum mechanics. Now, since you're here in this session, you most definitely have heard of quantum computing, but let me use this opportunity to recall a couple of basic facts about the quantum computer. In principle, what we say is that the quantum computer is faster than a conventional computer. But I think all of you have probably heard that a quantum computer is faster for specific tasks. So it's not just in general a faster computer, but for very specific tasks, the quantum computer can be, faster in the sense of really much more faster. Really faster in a really revolutionary way. And therefore, the key goal of quantum computing is not simply to run something slightly better or faster, but to achieve quantum supremacy. Quantum supremacy is the goal where we can solve a problem on a quantum computer that we basically could never solve on a conventional computer, or at the very least where we would need a vast amount of computational power and computational time on a conventional computer. Yeah, roughly imagine you have a problem that runs on a quantum computer for a couple of hours, but you would need maybe a year running a whole supercomputing center to do the same. Yeah, that would be quantum supremacy. And in principle, it's clear that this can be achieved, but we should understand that right now, quantum computers have very limited capabilities. This is because quantum computers are intrinsically sensitive to errors. Therefore, right now, we have what is often called noisy intermediate scale quantum computers. That's often also called NISQ computers. And in these NISQ computers, what we can do is quite limited. Nonetheless, quantum advantage or quantum supremacy has basically been shown for NISQ computers, but for highly specific mathematical problems. And what still remains to be done is to show quantum supremacy for a specific problem, that actually has an application. Now, given that fact, that quantum computers can run some problems much, much, much faster than conventional computers. One thing where quantum computers and global warming often intersect, or let's say where people consider that they intersect, is in this idea that quantum computers could be more energy efficient than conventional computers. And in some sense, that's obviously self-evidently true. Yeah, if I can solve a problem in an hour on a quantum computer, but would need to run a supercomputing center for like a year to do the same, of course, that would save energy. But I don't feel that this is necessarily really how we should envision the use of quantum computers and actually computing in general. If we use computing and computing power in general, what we do is we replace tasks that we otherwise would do in the real world. And normally we would expect that the computer, any computer, be it a quantum computer or a conventional computer, is more energy efficient than us doing the tasks in the real world. So if we transfer something from the real world to the digital world, we already save energy, and therefore using more compute power should on average be a good thing and save us energy. And what we should assume is adding the quantum computer in general to the overall computing capabilities will, create more opportunities to use computers instead of doing real life tasks, and therefore replace energy in this fashion without necessarily making computing itself more energy efficient. Or most definitely, it will not reduce the energy which we use for computing in total, since quantum computers will always add in tandem with conventional computers. And if we can do more, in terms of computing, we will use more conventional and quantum computers in total. And, if we now think about these specific problems that we want to do on a quantum computer, the specific problem which I consider interesting is solving kind of intrinsically quantum mechanical problems. And these are problems that appear if you study material science, can also appear if you study device science for, let's say, or device fabrication for very small devices, for microscopic devices. And here we would use computers to design devices such that we have more efficiency before testing and fabricating devices in a lab. And this would be one of the steps that would kind of be more energy efficient as we move things from the real world to using computers. In general, I think we can definitely be optimistic about the possibility that technology will help us to address the challenge posed by global warming. I mean, it's, I think, clear that already now, if we look at energy savings, but most importantly also production of electricity. Technology has a huge impact, and we have made great progress in terms of alternative energy sources that allow us the production of electricity without, CO2 creation. And the specific research direction which can have a huge impact here is material science. We see this, for example, in a very important way in the development of solar cells. In the last 40 years, the price of solar cells has basically dropped massively and made solar cells quite cheap today. And this has been really a triumph of material science and material fabrication. And probably this type of success can be repeated in other areas, most importantly in one of the remaining areas that we need to improve to kind of help us use alternative energy sources in an efficient way, namely when it comes to energy storage. And of course, the topic I'm talking about is the research and improvement needed on batteries. Batteries would be a topic where material science hopefully also can make a huge impact in the next 10 to 20 years. I mean, already if you look backwards in the last 20 years, there has been a huge improvement on every level, on the fundamentals of the materials, but also then on the way they get packaged and the price at which they can be produced. And we definitely can be optimistic that these trends kind of progress into the future. And maybe, it's even possible that we make on a more fundamental level new breakthroughs in energy production through maybe solar cells and energy storage in batteries, or maybe through other means like storing hydrogen or similar type of efforts. And the reason why I bring this up, of course, is that this is the field where we also feel that quantum computers can have the most direct impact. And it's because, as I mentioned before, progressing materials, needs us to understand materials and effects in materials on a microscopic level, which means on a quantum mechanical level. And it is here where we can use the quantum computer in a very interesting way. Yet, if we look at the timeline of using computers to progress material science and then progressing from breakthroughs in material science to actually mass fabrication, and this really going into production, we need to be realistic when we think about what quantum computers really can do, to solve or to help us solve problems related to global warming. Using quantum computers to advance material science is one of the key goals of HQS. And since this is probably going to be also the major way how quantum computers are going to affect the attempts to solve the problem of global warming, let me now talk a little bit more about how we think that quantum computers are going to be adapted, and more specifically got to be adapted in terms of improving material sciences. A lot of research on materials and in general on understanding quantum mechanical properties of materials is done in academia. You can actually see this already now if you look at what is done using supercomputing time in academic high-performance computing centers. They are order of 25% to 50% of the overall computing time is used to solve problems that are intrinsically quantum mechanical, or at least partially quantum mechanical. And I mean, this is because many of these problems are problems related to quantum chemistry or quantum metaphysics. Of course, there are also problems in particle physics that are not quite related to what we are discussing here, but they are still quantum mechanical. But clearly, you know, in these use cases in high performance computing centers, the interesting topics where you try to fundamentally advance what we know about materials and the use of computing power to do it come really together very nicely. And what makes this also really nice is that there's clearly an interest and the capability to host quantum computers in high performance computing centers. And on the other side, also a kind of specialist user base that even if using quantum computers would not be immediately super trivial and easy to do, you know, the user base of high performance computing centers would be, I think, very ready to adopt it. And this means that this is the way we think quantum computers will come into use. High performance computing centers will start, you know, to either first create cloud-based access, but then sooner or later probably also host their own quantum computers. The major use case of these quantum computers is going to be solving intrinsically quantum mechanical problems. And quite a lot of that is going to be related to material science. And specifically, actually, again, specifically, I mean, even more kind of specifically, the very first thing we actually think where it will really make sense to use quantum computers is actually related to a quite kind of subset of models, so-called resonant transfer models, that have been used to optimize or to understand organic solar cells and organic semiconductors more generally. And actually, we hope to bring this type of software into broad circulation, such that very soon, you know, quantum computers can be used to understand fundamental effects related to electron transport in kind of amorphous materials, amorphous semiconductors, organic semiconductors, and materials that hopefully, you know, at some point will improve our solar cells and the way we can use them substantially. And with that, I come to the end, and I want to thank you again for being allowed to, you know, voice my opinion on how we'll use quantum computers and hopefully how it will impact kind of the fight to reduce CO2 emissions in the near future. Thank you.